increases, our reaction rates will increase. The question is why? Okay, why do these reaction rates increase? And it really comes right back to those numbers of collisions and those effective collisions. Right, so there are a couple things that are happening when we increase or decrease temperature. So if we increase temperature, what is it going to do to the speed of the particles? Well, if we're going to increase the temperature, the kinetic energy goes up, right? So those particles are going to move faster. So our kinetic energy increases, the particles move faster. Right? Well, if they're moving faster, that's going to cause more collisions. They're going to just collide more often. We'll have more collisions. Right? So for example, let's say we have, two particles. Right? It's hard to see here. Okay, here are my pens. These are my particles. If they're moving really slow, they're not going to run into each other very often. But if we speed them up, okay, they're going to run into each other more often. So just by speeding them up, right, the chances of collision are going to increase, and we're going to get more collision. So that's one part of it. But there's actually a second part. Remember, to have an effective collision, there's two parts to an effective collision. One, correct orientation, but two, they have to have enough activation energy. Well, if we increase the energy that the particles themselves have, more of the collisions are going to have that activation energy for the reaction to occur. So the particles themselves have more energy. If they have more energy, more particles have the activation energy needed. Which means there'll be more effective collisions. Our fourth factor is going to be surface area. So when we're talking about surface area, we're talking about where the actual collisions can occur. So let's say that we have a solid sphere. The only place that this reaction, if I put this in something that it's going to react with, I don't know, maybe we put it in a beaker with sulfuric acid or something, the only places that collisions are occurring are right here on the outside. There are no collisions occurring in here. Right? So this is my surface area. So this is where the collisions can occur. Right? Now, what if I take this sphere and I break it up? So let's say that I cut it in half and then I cut it into quarters. So now I might have something like, ooh, that's not what I wanted. Disregard that. Okay, so I might have a quarter here, quarter here, quarter here, and a quarter here. So instead of having this solid sphere, now I've cut it up. Well, what have I done to my surface area? Well, all of this area that was originally exposed is still there. But now, what have I done? Well, now there's area inside that was not available before. Okay, so all this area in here, all this surface area is now exposed, so collisions can happen here. Well, if we cause more collisions, that means we're going to have a faster rate. So as we increase surface area, okay, our reaction rates will increase. So now, okay, this is actually a problem in the food industry. So flour, like you cook with, bake with, all right. What that is, it comes from grains, and we bring that grain in from the fields, from the farms, all right. And you have you know what grain looks like? It's like rice, that's a grain, all right. To make flour, though, we have to take that grain and we actually have to grind it up. Well, it turns out that flour is actually very flammable. Okay, but it's only flammable, well, it's highly flammable in powder form. So if you get it into a powder form, it's highly combustible, and if there's a spark, you'll cause a huge explosion. All right, and the reason that you'll cause that high explosion is because the dust particles, there's so much surface area, all right, that the reaction happens just like that. So you have to be really careful with this. So dusts and powders react faster than a solid. Okay, so right, in other words, the bigger the surface area, right, the faster the reaction is going to happen. Now the last factor that we're going to talk about are catalysts. And we're only going to spend a few minutes with catalysts right now. And when we talk about catalysts, these provide an alternative reaction path with a lower activation energy. And if we have a lower activation energy, that means we'll have a faster rate of reaction. And we're going to talk about that in a minute. A catalyst can also correct orientation problems. So let's talk about these two things. So let's say that this is a catalyst for some reaction. Let's say this is the catalyst for a reaction between AB and CD. Okay. So what this catalyst will do, okay, is we put it in with our reaction and it'll start to catch some A and B, some AB. Here comes our CD, and it's coming in at the incorrect angle, and it catches it like this. Normally that would be an ineffective collision, and these would just bounce. But with this catalyst, it's going to correct that orientation problem. It's going to swing the D up into here. It corrects that orientation issue. These can now react, all right, and the reaction happens. So what we're doing is we're taking an ineffective collision and making it effective. So we're increasing the effective collisions. This is going to make it a faster reaction rate. All right, this is what I mean by correcting orientation problems. The catalyst can also decrease activation energy. And what a catalyst can do, or often will do, is when it actually catches the reactant, it will either weaken or break the old bonds. Okay, because of this orientation. All right, and if that happens, it reduces our activation energy. All right, so the particles need less of it, and this reaction will happen faster. So that's in general what our catalysts are doing. There's a catalyst for every single reaction. They're all different. There are thousands and thousands and thousands and thousands and thousands of different types of catalysts. All right, and they are specific for reactions. So cobalt chloride is a typical one that we use for some reactions that happen here at school. All right. But we'll have to use a different, if we're doing a different reaction, we're going to have to use a different catalyst. All right. Catalysts are important in our bodies, so there are a lot, proteins act as catalysts to increase all those organic reactions that are occurring. All right, that dehydration synthesis and the production of our DNA and proteins and all those all have catalysts that are important, right, to speed up those reactions in our bodies. Okay. All right. So those are our 5 factors that affect our reaction rates. Right. The last thing I want to talk about today is another graph, and these are called potential energy diagrams. Something's squeaking in the walls. Right, so these are either going to look like this. I've got 2 graphs. They're either going to start low and go high, or they're going to start high and they're going to go low. Okay, and we're going to look at let's look at what happens if we have A plus B going to AB. So this is going to be energy changes. This is a graph, and it's going to be over time. So we can get numbers during a reaction. So let's go ahead and label this. So this is before the reaction occurs. So this is where we have reactants. This is where our AB would be. Okay, this is where our reaction has gone to completion. So this is where our AB would be. Okay, this is where our product would be. So this is my reactants. These are my products. Right now, so we can actually get the potential energy of our reactants off this graph. This distance from here to here, right? So if I read it off the graph, this would be the potential energy of our reactants. This distance right here would be the potential energy of the products. Okay. It's a graph, so I just go and that would give me the potential energy of my products. The distance from where we start, from the reactants, to the top of this hill. So let's just go. So this distance right here, this is the amount of energy we need to get the reaction started. This is called the activation energy, or E subscript A. So EA is our activation energy, okay, which is used to break those old bonds. Okay, so that's my activation energy. The distance, okay, the distance between our reactants and our products, so this distance here, this is called the delta H, or the heat of reaction. And we've talked about that. Okay, it's the heat of our reaction. Right here at the top, okay, where the particles have collided together and they have the activation energy necessary for the reaction to occur. At this point right here, this is called the activated complex. Okay. So right here at the very tippy top of this curve is where both A and B have collided. They do have enough energy for the reaction to occur, but the reaction hasn't occurred yet. Okay. Now, at this point at the activated complex, there are two possibilities. One, the reaction occurs and we come down the hill and we produce our products. The second possibility is the reaction doesn't occur for whatever reason. Maybe for whatever reason the old bonds don't break. Okay? All right. The second possibility is that we'll come back here, right back to reactants. So there are two possibilities once we get to that activated complex. Now, in this case, the potential energy of our reactants is less than the potential energy of our products, which means to go from reactants to products, energy is absorbed. Which means this is an endothermic curve. This is an endothermic curve. Our products have more energy than our reactants. Energy is absorbed. Okay, now let's look at this one. This is really just a mirror image of this guy. Okay. We're starting with AB and going to A plus B. Okay. So now these are my reactants and these are my products. This would be the PE of my reactants. This would be the potential energy of my products. This distance would be the activation energy, E subscript A. This distance is my delta H. This, again, is my activated complex. Now, in this case, the potential energy of my reactants is greater than the potential energy of my products. So as we go from reactants to products, energy is given off. If energy is released, that means this is going to be an exothermic curve. Now, in reality, they're exact opposites of each other. So let's just go back to here. If I read in this direction, if I go from left to right, okay, that is an endothermic curve. But if we read it in reverse, now we're going from high to low, that would be an exothermic curve. These are going to be, they're exact opposites of each other. All right? They're exact opposites of it. Now, what's important here to know is to look at our delta H. Our delta H, the actual numeric value of delta H, doesn't change whether we're going forward or reverse. All right? The delta H doesn't change. What changes is our sign. Remember, a negative delta H, okay, tells us that it's exothermic. We've talked about that before. All right, so if we subtract the potential energy of the products minus the potential energy of the reactants, if it's negative, it's exothermic. Well, we know that this is exothermic, going from high to low. So if our products are low and this is high, delta H is going to be negative. If it's a positive delta H, it's going to be endothermic. Okay. So the delta H, the magnitude of delta H is the same for the forward and reverse reactions. What's different is the sign. Alright, so these are our potential energy diagrams. Alright, and it's really just charting the energy changes as the reaction is occurring. Alright? Okay, so that's where we're going to stop for today. We will pick up with kinetics next class, and we will see you soon.